Welcome back, my fellow duplicants, and a very Merry Christmas Eve to you. Now, today we're going to take a look here at liquid oxygen. Now, this is something that we have covered, many times before. As I was actually looking back through the whole history of things that I've done with liquid oxygen, it turns out we've done about 9 videos on this. We used to call these things hydrogen bubblers back in the day, and we learned some really cool things about thermodynamics, about concurrent and counter-current flows and how that actually works to where we can kind of make things more efficient. I don't know. It was one of the breakthrough moments that I felt where this game was actually teaching me something besides just how to play the game. It was actually teaching me some science, and that was pretty cool. There's also another thing we did in here where we did a community design challenge where we actually came up with different ways to make liquid oxygen. Again, this was way before a lot of the cool new tools we have now with automation and, all the different materials that we now have. We doing PewDiePie, get off my video. So how this is going to work is we have 3 parts that I'm going to cover right here. I'm going to use a thermal regulator here, and I'm going to see if I can accurately predict how much liquid oxygen I can produce with a system like this, which isn't going to be a lot because the thermal regulator is only going to be capable of so much. And we're also going to look at a method of actually deleting the heat, which is going to be using a carbon skimmer to actually drop the temperature of the water that is running through here. So we're going to consume a little bit of carbon dioxide, but we're also going to gain a little bit of dirt, polluted dirt from the water sieve here. So it's a way of converting one thing into another thing and losing a bunch of heat in the process. Now, we actually have a real reason to make liquid oxygen because we can use it to power our rockets. But then again, we can also pretty much just get there on oxalite if we wanted to do that, and then eventually come back with supercoolant and really power up a lot more liquid oxygen and potentially liquid hydrogen and all of that good stuff. We're going to work our way up to that goal. So once we have a little bit of liquid oxygen here, just like we've seen with some of these other community design challenges in the past, once we have liquid oxygen, we're going to use that to seed a more powerful system, which is going to use a thermal aqua tuner, which can delete a lot more heat, or shall we say it can transfer a lot more heat, and then we can delete the heat out of that. And then the final system here is going to be the same sort of thing, but actually using supercoolant and potentially a steam turbine in order to delete that heat there and also reclaim a little bit of the energy that goes into the system. However, to even have a chance at making this thing work, we gotta do some math first. So let's bring on the classic spreadsheet here. So I've done some math already to kind of get everything up to. So you weren't watching me work a spreadsheet here for like an hour. Laid out all my different equipments up here and the variables and the numbers or whatever. And we're also working in Kelvin up here, so that's also why these numbers are going to look a little weird. But essentially what I'm trying to do is answer the first question here. How much heat can the carbon skimmer delete? So at a given temperature, we're going to bring it in at, I believe this was 90 degrees Celsius. And then per kilogram, there's that many DTUs in there. So duplicant thermal units. And then the temperature out is going to be a set temperature, which I believe is 40 degrees Celsius. So therefore, the difference between this and that allows us to delete 208,000 duplicant thermal units every second. And that's only if my math is correct. We'll see. When we go to run it, we'll find out if I'm terribly wrong or not. So the next question I need to answer is how much heat do I actually need to remove from oxygen in order to make it into its liquid form? So essentially, I gotta convey that heat away. So coming in at 50 degrees Celsius, I have this many DTUs, and leaving at negative 183 degrees Celsius, I am going to have that many DTUs. So therefore, I have to convey away in that 1 second. If I wanted it to go from way up here to way down there, I would have to take a total of 235,000 DTUs out of that 1 kilogram of oxygen. So that gives me a number to work by. Essentially, what I'm using here is to figure out, okay, this liquid oxygen could, or at least with this carbon skimmer, I could potentially convert 887 grams of oxygen per second all the way from its liquid numbers. All right, so question 3. So the carbon skimmer can handle how many grams a second of oxygen? Well, if we take question 1 divided by question 2, essentially what we get here is 887 grams of oxygen for every 300 grams of carbon dioxide that we consume. So that just covers the carbon skimmer, right? So that's our way to delete heat out of the system altogether. However, what we're actually using to transfer heat from here to there is the thermoregulator. So looking at the thermoregulator, how much heat can the thermoregulator actually transfer working with hydrogen in its loop? Well, every time it runs through there, if it runs through at 1 kilogram per block, then the amount of temperature that it's going to drop is 14 degrees Celsius, or it's going to transfer that much. So that's a total of 33,600 DTUs. So once we figure that out, you can transfer enough heat to potentially handle 142 grams of oxygen per second. So what I'm understanding from this is that our carbon skimmer is not going to run 100% of the time, mostly because it's not going to be saturated. However, we can only run roughly maybe 140 grams a second of oxygen into the system if we don't want it to continue to heat up. Alright, so let's take a look at my system here. You can see that I have a thermoregulator, water sieve, carbon skimmer, and a little bit of a gas reservoir. So let's just take a look at the heat transfer loop. So this thermoregulator is going to kick out a temperature here, and that's going to go up, and that's going to go through some nice radiant gas pipes. Now I might throw some you know, temperature shift plates back there just to kind of add some thermal mass and even things out, but whatever. That's going to cool down the oxygen that's over here into its liquid form. And if that temperature comes back at above a certain temperature, or I guess if it comes back below a certain temperature, it's actually just going to loop back through. So it won't keep going to the point where it actually accidentally turns into liquid when it runs through the thermoregulator. So if we take a look at the hydrogen, it will turn into liquid at negative 259 degrees Celsius, which is going to be kind of hard to reach, but whatever. Okay, so if the temperature here is above negative 245 degrees Celsius, then it should kick back around. Because if it was to continue into here and then back into the thermoregulator, below that temperature, it could potentially be cooled to the point where it turns to liquid hydrogen, which would break the pipe right here. You don't want that. So that's a temperature check, and it should just flow back around. Oh, and I can't remember which one's going to get priority here. Dun, dun, dun. I don't know. That might be a problem. I just can't remember everything. All right. All right, as far as the liquid loop, what I'm going to do is run this water over here. So that's going to be clean water, and it could also be polluted water as well. And that's going to find its way into this loop and run down here. So all that's going to do is try to maintain a temperature that's like 90 C or right around there. So it's going to be kind of hot over there. So if the temperature hits above 90 degrees Celsius, then it's going to run from here into the carbon skimmer. And everything that runs through this water sieve will come out clean. So I need to have some carbon dioxide that's just over here ready to go. So let me go ahead and just make a little bit of that over here. All right, so there's a bunch of carbon dioxide. Perfect. We're going to give that a nice little gas pump. Boom. And all that's going to do is feed into here. Power-wise, you can see that there's really not a lot required to run this. It's actually pretty simple. We're also going to need oxygen that's going to flow into here, so I got to take care of that. See, that is at 46.9. What I actually want that to be is at 50. So that's going to be 323. There we go, 50 C. However, that's going to have a gas valve. That way we can meter, you know, anything that's coming into this over here. And I'm going to use a normal gas vent rather than a high pressure one, because that way it'll be kind of like self-metering as far as how much pressure builds up inside of here if we're not down to temperature just yet. I'm going to set this to 0. There we go. Actually, we can go ahead and just bring in like just a little bit. Okay, there we go. That was just a little bit. That's the wrong valve. Ah, problems. I wanted a gas shutoff valve here. There we go. And I wanted to fill this area with hydrogen. Like 2 kilograms of it. Bam, there you go. I'll also fill this area with hydrogen as well. So that's all ready to go. Okay, let's turn that off for a moment. Let's see how this thing runs over here. Okay, so I got that hooked up wrong. Go figure. And that's not what I want either. What I really want is to have... What am I doing here? Vacation brain. I got a full vacation brain going on here. Okay, so you can see how things are getting past here. That's not what I want. What am I doing here? In and outs, in and outs. There we go, that's what I wanted. Because this has a priority of 1, that is a priority of 2. Okay, good. Keep forgetting everything I need to know. Alright, so if that is below that temperature, then yes, then it needs to run. Okay, there we go. Not above. I don't know what I said before. Whatever, just go along with it. Alright, where's this tutorial video that I made? I know I made one. There it is. Today we're going to learn a little bit about pipes and how... I gotta watch my own tutorial video just to remember how to do pipes. Alright, give me a minute. 15 minutes to be exact. Always giving pipe a direction. Yeah, okay. Aha, that's it. That's the trick, that's the gap right there. See, I knew I figured this out beforehand. Not that I ever remember my own solutions. Jeez. Okay, so that's what I wanted. No, it's because this one has a... Darn it. Because there's 2 directions. So if I do this... Yeah, okay. There we go. Speed up the game a little bit. So what I'm doing here is I'm using the gas reservoir to average the temperature that's running through here. So the hydrogen can only be the sum of whatever all the gas is inside of there. So right now it's at 14.5 degrees Celsius. So by doing this number, I'm more or less controlling the temperature of the entire loop. So I want to turn this off before it fills up. There we go. So now it just runs and runs like this. Meanwhile, it's getting colder and colder, but there's more heat that's going to be around here. So I got to get rid of that heat. It's not going to be 100% efficient either because this is in the same area as where the heat is going to be. That actually might be a better idea to move that somewhere else, but we'll see how this works for right now. Okay, so for the liquid, I just need some water. Well, where do I get some water? I don't have any water. Water 1, water 2, power, and then we're going to fill that with water. And then run an automation signal to that. So if this is, well, above 90 degrees, then it's going to kick out. So that's what I want. Yep, and I got a problem with my loops over there. Okay, so I think that's how I want to run it. Like this, to that, to that. Hey, hey, stop breaking over here. No, no. There we go. Insufficient resource. Okay, so auto sweeper. Yeah, it just keeps getting more complex. Here we go. Dun, 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 dun. Put that in. We're going to brush in some sand. And then we're going to dig that up. There we go. Delivered. So it doesn't use up any sand if you're just running clean water through it. But if we start to run dirty water, it will. That's something that's actually really quite important. Okay, so this is up and running. Now if we take a look at the temperatures here, we should get some sort of idea of what's happening. And it might actually be worthwhile at some point here to get rid of these tiles and actually allow some of that heat out. But I don't know, I think they might be self-regulating considering they have a source of something that's running in there. So we're going to disable that building. So now it's just running around and around, and it's running nice and quick now. That's what we wanted to see. So this is going to soak away the heat that's in here that's being given off by the heat that we're sucking out of this side over there. Now this is going to take a while to get down to temperature because it's got a lot of hydrogen that's in this loop. So there's a ton of thermal mass that's kind of running here. Alright, so I'm running the game ultra fast. Here we go. Let's take a look at the reports. Whoops, not that. The reports here. Previous day, 150 kilojoules, not a lot. 161 kilojoules, so actually that's fairly reasonable for what we're looking to do with this. Because right now the only thing that's running is this thermal regulator. And we're just about down to the point of turning this oxygen into liquid. It's at negative 170 degrees now. So what I'm looking for is 183. So, alright, now we should start to see some stuff here. Let me just... Well, the hydrogen is at the correct temperature. However, the oxygen has not yet responded to that temperature just yet. Let's take a look at diamond real quick. Low specific heat capacity, high thermal conductivity. Okay, so what I'm going to use here is some temperature shift plates made of diamond. You can dig that up from down in the base. I'm trying not to use anything that we couldn't get our hands on earlier in the game. So this is just steel. Everything in here is steel, you know, maybe gold, but I'm avoiding the really high-end materials. So no niobium or no thermium. Diamond. Oh my gosh, where are you? Oh, all right, at the very beginning. Okay. All right, so we'll just put diamond across the top there. And that is going to be interesting. Now what I want to see is that if this temperature here does go below a certain number, that it will just start to recirculate. So rather than go all the way down to negative 245, I'll remember that. I'm just going to check it at negative 200. How about negative 190? Let's see what it does. So at this point, you can see it now shut off the thermal regulator because no gas was flowing through it, and then it started to circulate back around. So if we run this a little bit faster here, see? Yeah, so it's working perfectly. Excellent. All right, we need to wind this thing up for a couple more cycles here. It'd also probably help if we would pressurize the amount of oxygen over there, because it's only at we only have 18 grams of it. So we're going to bring it up to maximum pressure. So now with that extra gas pressure in there, you can see the hydrogen's quite a bit warmer. It's gone up to, you know, negative 23 instead of being all the way down there at 200. Oh, and this thermal regulator is definitely the wrong one. Oops. I want to make that out of steel. Nice and conductive, and it has a much higher overheat temperature. There we go. Alright, so this is going to take a long time. There's a ton of thermal mass that we have to work through, and that's not a very fast piece of equipment, so maybe in 20 cycles or so. So this is where having more thermal regulators that you could potentially use at different temperatures of however much hydrogen you have would make the startup of this quite a bit faster. Actually, I think we'll die of old age before this one actually gets up to temperature. So I'm going to get rid of this diamond in here. Yeah, see, that's speeding things up quite a bit. So get rid of that, clear the floor. Okay. See, now it's actually going down. And you can see that we're slowly going up in temperature over here on the left. Slowly. And the water is slowly going up in temperature. So it's at 20. Then it just went up to 0.2. It'll go up to 0.3 eventually. There it is. All right, this is more reasonable. It might be like 10 cycles rather than 10,000. So while this is running, you can see my new battery setup over here. Yeah. Just have a whole bunch of these hydrogen generators. It's kind of a good way just for experimenting. Bam! Look at that. And I can actually just go in here and just turn those off. That way I don't get any sort of false readings on the power. I should probably hook all those up to the same one, but for science. And it doesn't require any duplicates. Not like any are left alive. You might be seeing some of these sensors over here. I don't know, and they're just there. No real reason for them at the moment. What else do I got going on? Well, I got a little bit of 3D printing. Captain America is actually printing up today. New camera angle. High def too. That'll be a fun time lapse. I've been working on a filament calibration guide. Printer guide. I don't know, the whole thing's ballooning into a much bigger topic, but yeah. Once you get things set, you can get like nice, consistent results. Really good. Speed up today, hydrogen. Please. Alright, so it looks like at cycle 20, we're potentially going to get down low enough in temperature where we might see some liquid oxygen here. So I'm going to be collecting my data over here on my spreadsheet, and we're going to kind of see just how efficient we are cycle by cycle. Come on, give me some liquid oxygen. Actually, we're probably going to see right off the bat that there's going to be a lot because it's high pressure. And then I have the inlet metered over here to be 140. No? Yeah, no, maybe? Only the top. Oh, I think I saw a little bit. See, the pressure's going up because here's what's happening. Turn that off for a little bit. I have all this extra oxygen over here that's just ready to find its way in. And then it drops down, evaporates, and kind of heats up a little. It heats up and evaporates. So the pressure keeps going up and up. But there is a little bit of liquid oxygen that's forming there. And that is why I have this down here. So I could say only when this is above, let's say 10 kilograms of liquid oxygen, will we ever go to pump it in. Because if we were to pump it in and it would be too close to its boiling temperature, when we go to kind of move it from one spot to the next, from this system to that one, you could potentially just blow up the pipes in the process. Maybe that even should be like 20 kilograms or something. Ooh, it's starting to accelerate. You can see it just dripping, dripping, dripping. And this is the spot where it's going to be the highest temperature here and the lowest temperature there, so that's actually pretty good. Although I'm not sure it matters in this small of a space. But yeah, there it is, a little bit of liquid oxygen. It's not sticking around just yet, but it'll get there. So all of the oxygen's moved from here into there, and what I should be left with here pretty soon is going to be a vacuum. It's kind of surging a little bit. If you take a look at the oxygen overlay, that's what it's doing. So the reason is because these tanks and pumps and whatnot are not cold enough yet. Okay, so if this is above 10, we should start to be able to pump it in there. All right, so I'm going to set this to 140 now, and let's see what happens. Maybe I won't track the numbers exactly. I don't know. We're just going to see. The temperature of the hydrogen inside of here is really, really cold. I'm going to bring in some more oxygen, and this oxygen should just flash right to liquid. You can see the pumps running every once in a while. So now the hydrogen has actually slightly increased in temperature. It's at negative 190. We can kind of track the temperature here. Yeah, it's slowly increasing, so I don't think it can quite handle the amount of oxygen I'm throwing at it. It's not quite as efficient as we'd calculated. It probably has everything to do with this in here. Not to mention the mini liquid pump will actually bring a little bit of heat into the system. So it's got 500 there. Hey, didn't I turn this off? Yeah, crap. You know what? I don't think it matters. I could probably just leave this on full and it's going to process what it's going to process. Alright, so we're at the beginning of 26. And here's where I'm going to log things for about, oh, I don't know, however many cycles I go. Alright, so I ran this for several cycles now, and it's nowhere near as efficient as it possibly could be. So you can see that I got 79, 72, 93, 55, 76. That's a fair bit lower than what I should be getting right there. So that is actually grams per second. The other thing I'm noticing here is that the temperature inside of this pipe is not going lower than the oxygen itself. So it's actually not getting as cold as it could be. So I think what I'm getting here is some inefficiency from the soak into this gas reservoir. So I'm going to rework this and then try to encapsulate that in some nice insulated stuff to see how that changes what's going on. So if I get rid of this floor down here, and for the sake of this experiment, I'm just going to go ahead and use the best stuff we have, which is insulation. Not that you would have that at this point, but you get the idea. I just want to control the variables. And then over here, I'm going to put a thermal regulator, and then that's going to do this number. So what we should see is that the temperature over here works its way back down. And it is. Slowly. Okay, so rather than wait forever to get that down, let's go ahead and just fill that area with some nice cold gas. Actually, we're just going to make it a vacuum. Well, that definitely helped a little bit. It's ramping up a little bit. Okay, so far the test results are kind of ramping up a little bit. So I'm at 83, 91, 96, 100. Let's see what happens. I'm going to let it keep running for a little while. 140 is about what we're looking for. It doesn't look like I'm going to get any better than 100. It's hovering right around 95 to 100, which isn't bad, but I think we can do a little bit better. So if I turn this off and we just let it run for a little while, try to let this hydrogen get nice and cold, that should allow the temperatures to separate a little bit more, which would make it more efficient when we go to cool it down in the first place. You know what? And then rather than have this set to anything, we'll just have it set to 1 kilogram. You know what? Maybe I just get rid of it. Okay, so now, okay, this is interesting. So now it's gotten to the point where it's 238. Oh, it's not to the point where it's too cold yet. Go faster. Okay, there we go. So now, this is what I wanted to see. So what over here is still hot? I don't know. Some other things from some other places. It could also just be the tiles here, because these are made out of insulated granite. They're not perfect. Hey, something skipped by. Cold damage. That's not what I wanted. Make this negative 40. Oh, no. All right, so I'm going to set this to negative 235. Give myself a little bit more range so that I don't accidentally destroy my system. And we're going to turn that off because that was helpful. All right, so now I'm down to temperature. What I want to do is just bring in oxygen. I'm going to start it off with 100 grams. No, let's do 120. Let's see what happens. Let's see just how much I start building up here. So this is flashing straight to liquid. So if I speed this up again, I'll be able to see what the temperature looks like. It's not quite keeping up. It's actually slowly warming up. So unfortunately, I don't think we're going to ever get to that 140 efficiency. Probably has a lot to do with these tiles and whatnot. So what can I get it to? 110? It seems to be balancing right at 100 grams a second. So the temperature of the hydrogen is not getting colder or hotter. It's like, ooh, maybe very, very slowly it's getting hotter. Maybe it's 99, but that seems to be all I'm going to be able to get out of this currently. So let's try one more thing. Even though I don't think it'd be available to you at this point. Maybe it would be, but we're going to put insulation down. This is going to give us our best thermal isolation that we can get. We'll see what happens with the hydrogen then. Yep, and right away, the hydrogen is getting colder and colder. So it was the tiles that was surrounding that. So a lot of the heat, even though this is a vacuum out here, it was actually going up into the hydrogen that's around this. So the liquid up there. So we saw an improvement when we isolated the gas reservoir, and now we're seeing another improvement when we isolated this from our chamber. So it'd be a good idea to have, if you just want to get the most out of it, which isn't, I mean, at this point, I don't think you'd really want, whatever. If you have a reason to run this with a thermal regulator, that would be one way to do it. You'd want to probably have some vacuum around this. See, the temperature is getting colder and colder. Let's see, at some point here, it's not going to flow over there anymore. Yep, there we go. You can kind of see it. So if I set this to 110, 132.3, how about 120? Yeah, it's still working. 130. Alright, so now we've reached the point where the hydrogen is starting to warm back up. So it looks like the best I can get out of this. There's some inefficiencies still. You know, I mean, this thing puts off a little bit of heat. So that's probably playing into it a little bit. But it's pretty close to what we calculated. Alright, so just to conclude here, turning oxygen into liquid oxygen in this setup right here, using a thermal regulator, we're able to achieve anywhere from right around 60 to 125 grams a second, depending on the setup and the materials used. And based on our calculation, about as good as we're going to get is 140 grams a second, because there just isn't any more energy that this thing can do, you know, just only having one of them. So what happens if I set this to above 1? Yeah, that'll be nice and efficient. You know, I might be able to get a little bit more efficiency if I just push this down. Negative 240. Ah, well, pretty close. So the other thing here is that all comes at the cost of 188 kilojoules a cycle, which really isn't that bad. Oh, and you know what? We never even got this hot enough to delete any heat out of this. So give me a second here. If this goes above, let's say 45 degrees. And at that point, so now polluted water starts to flow through. And what I want to see is the temperature of water go down. And what I see here is that 56.3, 56.2. By running that through, it is working. And if you take a look at the temperature of the liquid that's flowing out, yeah, see, polluted water is at 40 degrees Celsius. So it's completely possible to delete heat this way. If you take a look at the temperature of the equipment, it's slowly going down as well. So that works. But you're really not getting a ton of liquid oxygen. So at this point, what we're probably going to want to do is either take our liquid oxygen, run it up here, and try to run it through a more powerful machine, which is the thermal aqua tuner. And once we have enough of that, we might be able to launch a nice big rocket and potentially come back with some nice supercoolant, which should really allow us to transfer a lot more heat. So those will be in the next 2 videos though. Thanks for watching, guys. Hopefully you guys have enjoyed this little episode here of Oxygen Not Included. If I've earned your subscription, then thank you so much for that. Thanks for watching. Have a very Merry Christmas, and I'll see you again next time. Stay awesome, guys. Peace. Brothgar out.